Hello dear students, this video is for semiconductors, which is a topic of ISC physics. This is part 2. We are going to learn about electrons and holes in semiconductors, intrinsic semiconductors, extrinsic semiconductors, and difference between N-type and P-type semiconductors. Children, we have learned in the previous video about energy band structure of conductors, insulators, and semiconductors. You learned that when temperature increases, the valence electrons acquire thermal energy to jump to the conduction band. If they jump to conduction band, they leave a hole behind them. The deficiency of electron is seen as a hole. They leave a hole behind. You can see the holes in the figure. This is the deficiency of electron and is termed as a hole. It is considered as a seat of positive charge, having magnitude of charge equal to that of an electron. Let us study about types of semiconductors. Intrinsic semiconductor. A pure semiconductor is called intrinsic semiconductor. It has thermally generated current carriers. At temperature close to zero, there is no free electron. The silicon atom has 4 electrons in the outermost shell, which have made a covalent bond with the nearby silicon atoms, and these bonds are stable. At temperature close to zero, there is no free electron, so the semiconductor will act as an insulator. But at room temperature, the semiconductor thermal energy is gained by the electron, and it breaks one of the covalent bond, and it leaves the bond, and a hole is created, and we get a free electron. Let us study about the energy level diagram for intrinsic semiconductor. You can see that at 0 Kelvin, the valence band is full, completely full, and the conduction band is empty. Whereas at room temperature, we have a partially filled valence band and a partially filled conduction band at room temperature. What is the reason? The reason is that at room temperature, a few valence electrons, they gain energy and they reach the conduction band. Also, some bound electrons, they break the covalent bond, and under the effect of electric field, they start moving. Now you can see the concentration of free electrons and holes. It is given as Ne is equal to NH is equal to Ni. That is the free electrons, number of free electrons, and number of holes is equal to the total concentration of the intrinsic semiconductor. That means it is same, the intrinsic concentration is same as the number of holes and number of electrons. We have same number of holes and electrons in the intrinsic semiconductor. The concentration of electrons in the conduction band and holes in the valence band is equal. Now let us see the effect of temperature on charge carrier density. It is given as Ni is proportional to exponential power of minus Eg upon 2 kT, where Eg is the energy gap of the semiconductor and K is the Boltzmann constant. Children, because of less charge carriers at room temperature, the intrinsic semiconductors have low conductivity and they have no practical use. So an impurity is introduced in the intrinsic semiconductor, and this process is called doping. Doping can be done by many methods: by heating a intrinsic semiconductor along with the impurity atom, or by inserting the intrinsic semiconductor in a cloud of the impurity atoms. There are many ways to fuse a impurity atom into the intrinsic semiconductor. Now you can see here the semiconductor here has all silicon atoms, but here we have one phosphorus atom which has replaced one of the silicon atom. So this type of semiconductor obtained is called N-type semiconductor. Why N? Because phosphorus is a pentavalent atom. It has 5 valence electrons. The 4 valence electrons make covalent bond with the neighboring silicon atoms. Only 1 electron is free. So if we have more number of phosphorus in this, we will have more number of electrons as free electrons in this silicon crystal. So negative charge carriers are more, therefore the name N-type semiconductor is given. Whereas if you introduce boron, boron is a trivalent impurity. If you introduce a boron in a silicon crystal, then boron will make only 3 covalent bonds will be made, whereas one place with one silicon atom, one place will be empty, a hole will be generated. So here we will have majority of positive charge carriers. So it is called a p-type semiconductor. So these type of semiconductors which have impurity atom are called extrinsic semiconductors. Lead also makes a N-type of semiconductor. You can see the lead atom is present in the center. It is sharing its 4 electrons with the neighboring 4 silicon atoms. One donor impurity is free. 1 electron is gone free. So this is also called a donor atom. It is donating 1 electron, and this type of semiconductor is called N-type semiconductor. Similarly, if you add a boron atom, boron creates a hole in the covalent bond, and a hole can accept an electron. Therefore, it is called an acceptor impurity. It creates a hole. So this is a p-type semiconductor. Now, here you can see a 2D crystal lattice of silicon doped with phosphorus and boron. Now let us study what will be the type of energy band structure for an N-type semiconductor and for a P-type semiconductor. You see here, for N-type semiconductor, since it is a semiconductor, the gap is shown like this. Okay, although it is shown very wide here, but we don't have that much. It is only a denotion here that a wide semiconductor, a forbidden energy gap is shown. Anyhow, you can see the Fermi level also. Now, what is this donor energy level? Actually, the phosphorus, which is the pentavalent impurity, when it donated the electron, it donated 1 free electron to the silicon crystal. So that 5th valence electron, rather, or for all the N atoms, the 5th valence electrons of the impurity atoms, they occupy this discrete energy level just below the conduction band. And these are called donor energy levels. The energy gap with the conduction band is only 0.01 electron volt for germanium and 0.05 electron volt for silicon. The electrons, valence electrons which are present in this donor energy level, they get a small amount of thermal energy given to them. They jump onto conduction band, and your N-type semiconductor becomes a good conductor. So this is the benefit of adding an impurity atom. Intrinsic semiconductor has limitations. Its conductivity is very less and it is temperature dependent. Whereas for extrinsic semiconductor, the conductivity is improved due to large number of dopant atoms, and every atom gives 1 charge carrier. No dependency on temperature is left. And now here also, here in N-types and P-type semiconductor, we do not have concentration of electrons same as holes. In N-type semiconductor, concentration of electrons is more, and for P-type semiconductor, concentration of holes is more. So see the energy level diagram of P-type semiconductor. In this semiconductor, we have a trivalent impurity, which is creating more number of holes, more number of acceptor atoms. So the acceptor atoms, they occupy a discrete energy level just above the valence band. So in a n-type semiconductors, the electrons are the majority carriers, and the concentration of electrons in the conduction band is nearly equal to the concentration of donor atoms. Whereas for a p-type semiconductor, the majority carriers are holes, and the concentration of donor atom is nearly equal to the concentration of holes, charge carriers. Okay, so this is the energy level diagram for a p-type semiconductor and an n-type semiconductor. Now see the electron hole concentrations for n-type semiconductor and for p-type semiconductor. Let us study the difference between n-type and p-type. N-type is obtained by doping an intrinsic semiconductor with a pentavalent impurity, p-type with a trivalent impurity. In n-type, electrons are majority carriers. In p-type, holes are majority carriers. It has donor energy levels very close to conduction band. It has acceptor energy levels very close to valence band. When temperature is increased, these semiconductors can easily donate an electron from the donor energy level to the conduction band and contribute in the conductivity. Whereas for p-type semiconductors, when the temperature is increased, they easily accept an electron from the valence band to donor energy level, and we see the current carried by hole, that is called hole current. This is the distinction between intrinsic and extrinsic semiconductor. For extrinsic semiconductors, two types, n-type and p-type, conductivity is greatly increased, whereas for intrinsic it is very small. So children, that is all about semiconductors part 2. I hope you learnt well. Thank you.